Hello and welcome to our lesson on trig equations, our final lesson or final topic for this module, where we're going to kind of put together all the stuff we've been talking about so far. So the idea behind solving trig equations is that we're kind of merging the identities that we've talked about with algebraic skills that we've learned to solve. So the identities, all of those identities, and we're not going to see all of them here, but they could eventually come into play, combined with our standard algebraic solving methods, are going to be useful in solving trig equations. So we're combining all of it, okay? Now it's important to remember that when you're looking for the solution to an equation, you're looking for a value that when you plug it back in makes that equation true. Now trig functions are periodic. So if they're periodic and they just continue to repeat over and over and over, then what we could see is an infinite number of solutions for our trig equation. So since our trig functions are periodic and they just keep repeating, we could have this solution that repeats as far as our trig function repeats. So it's not unusual for a trig equation to have an infinite number of solutions. And the goal for us is going to be to find and describe all of the solutions. So using the unit circle is going to help us establish, let's say, one or two solutions within a full cycle, like within a 0 to 2 pi window. But if we were to keep going forward, or to even work backward in negative angles, then those answers are going to repeat. So we have to make sure we find a way to describe all of the solutions. Okay, all of them. And there's going to be a lot of techniques that we're going to look at, but one common approach, one general strategy, especially if there's just one trig function involved in your equation, is to isolate, to get that trig function all by itself on one side of the equation. So let's try to get the trig function by itself and see if we can't solve from there. Okay, it's when we start introducing multiple functions. So if we have, for instance, a sine and a cosine in our equation, where that's generally the identities will come into play. Okay, so let's look at a few where we can solve by isolating. All right, so for example here, if I wanted to solve by isolating, I want to get the cosine, the trig part of this, all by itself. So I might start by subtracting 3 from both sides, which would leave me a negative 6 cosine x equal to a negative 3. And then I could divide both sides by negative 6, excuse me, which means the cosine of x would be equal to a positive 1/2. And from here, we've sort of done this concept before. We're looking for the cosine of some angle to be a half. Well, if we go to our unit, oops, went too far. If we go to our unit circle, where is the cosine of an angle equal to a positive 1/2? Well, that happens at pi over 3. We have a cosine of 1/2. And it also happens here at 5 pi over 3. We get a cosine of a half. Okay? Now, let me ignore this one for a second, right? It's going to happen at pi over 3. And if we go a full circle, pi over 3 plus another 2 pi, it's going to happen again. And if we just keep rotating around the circle, we're going to get that pi over 3 solution plus 2 pi plus another 2 pi. So what we can say for this one is that one of our solutions is going to be pi over 3 plus 2 pi n number of times, and n just represents the number of times you would be going around the circle. So one of our solutions is pi over 3 technically plus its 2 pi n number of times. That's an infinite number of solutions. So that's what one set of our solutions will look like. Now, the other solution at 5 pi over 3, the exact same thing is happening, right? I have this 5 pi over 3, and then if I go a full circle, that's going to happen again. So I could say 5 pi over 3 plus 2 pi n number of times. But if I leave out the other direction, I'm kind of leaving out some solutions. So think about like on an x and y axis, right? The sine curve, or what are we looking at? Cosine here. Cosine curve, right? If we started at 0 and only went in the positive direction, we're leaving out the entire piece of our graph on the other side. So what I'm trying to say is we have the sine curve, right? Right now or cosine curve, I'm only looking at this side of it, but there's a whole other side over here on the negatives. So instead of referring to this angle as 5 pi over 3. Just to incorporate the negatives here, I'm going to call this angle its coterminal angle, which is a negative pi over 3. So we have positive pi over 3 here, we have a negative pi over 3 here. So we're going to call this angle negative pi over 3, and then again, if I just keep adding 2 pi n number of times, I'm going to land at that same spot. So those are going to be two sets of infinite solutions, pi over 3 and negative pi over 3, plus 2 pi n number of times. So that will capture both of those angles where the cosine is equal to a half. So we're going to say that x can equal, we can say it separately, pi over 3 plus 2 pi n number of times, and again we can say negative pi over 3 plus 2 pi n number of times, or because it's the same value but one's positive, one's negative, we can simply condense that and say plus or minus pi over 3 plus 2 pi n number of times. Okay, so that's how we can describe all of the solutions to that equation. It's a lot. It's a lot. More than a lot, it's infinitely many. Okay, let's try that process again. Let's try to isolate the secant of 3x here. So the first thing I would do is add 1 to both sides. Then our secant of 3x divided by 2 is going to equal 1. And then to get rid of the divide by 2, I'm going to multiply both sides by 2, so that the secant of 3x is going to be equal to 2. So what I'm going to look for now is the secant of some angle here. It's going to be 2. So secant of some angle is going to equal 2. So let's go up to our unit circle. Secant, if you remember, is the reciprocal of cosine. So I'm looking for the reciprocal of cosine to be 2, and we're at the same place, right? So this is where the secant's 2, the reciprocal of cosine is 2, and positive 2. And that happens here again. So we actually are looking at the same two spots. We're looking at pi over 3, and again, I'm going to call this negative pi over 3 just to capture both. And a full circle will just take me back to the same spot again and again. And so we're going to say here, this time I don't have just an x, I have a 3x. So we're going to say 3x is going to equal plus or minus pi over 3. And then we're going to add on another 2 pi n number of times, because every time we go a full circle we land in that same spot again. So in this one I have to go an extra step to solve for x. To get rid of that times 3, I'm going to divide 3. So x is actually going to equal plus or minus pi over 9 and 2 pi over 3 n times. Okay, so that's our solution set for that one, which is just crazy, right? Seems like, what are we doing here? I don't know about you, but that looks like a foreign language or something. All right, let's try it again. So we're going to try to isolate here. First thing we're going to do is add 1 to both sides. So the tangent squared x is going to be equal to 3. And then how do I get rid of the square? Well, just like everything else, right? Opposite of minus 1 is plus 1. Opposite of times 6 is divide 6. The opposite of taking this, or squaring, is taking the square root. So if I square root both sides, then the tangent of x is going to be equal to plus or minus the square root of 3. So we're actually looking for two things. We're looking for where the tangent of x is equal to a positive radical 3 and where it's equal to a negative radical 3. So where is the tangent of x equal to radical 3, and where is the tangent of x equal to a negative radical 3? All right, let's go back to our unit circle. So tangent is y over x, which means I have to be able to divide a radical 3 over 2 by a 1/2 in order to end up with a radical 3. So that's going to happen, wouldn't you know it, in the same couple of places. So at pi over 3, and that one reoccurs, so it's positive. I'm just looking for the positive one first. Pi over 3, and that reoccurs, negative here is going to make a positive. So at pi over 3, and every 180 degrees from there. So if I go pi over 3 and then 180 degrees, I'll get another solution, and then 180 degrees, another solution. So I actually don't have to state this for pi over 3. If I just say pi over 3 plus 180 degrees, or pi radians. So I'm going to say pi over 3 plus pi n number of times. So then I would start here and say, okay, every pi, oops, got another one, and then go around pi again, oops, got it again. Okay, so that's going to capture that 4/3. So that's the positive version, pi over 3 plus pi n. And then we also need to know where it's negative. So where is it negative? Same values, right? I still want that y divided by that x, but I need a positive divided by a negative. So that's going to happen here at 2 pi over 3, and then it's going to happen at its counterpart down here at 5 pi over 3. But again, that's 2 pi over 3, and then plus pi radians, or 180 degrees. So if I just say 2 pi over 3 plus pi n times, then I will capture that solution set. So this is where it was positive, and this is where it was negative. So positive, x was going to be excuse me, pi over 3 plus pi n number of times, and it was positive at, I already forgot, 2 pi over 3. 2 pi over 3, and again, every 180 degrees, or every pi radians, n number of times. So we have another two more infinite sets of solutions for this one. And that last line was just terrible. Okay, that looks a little bit better. All right, so isolating. There we go. Hopefully this is not so bad. Let me get rid of my mess here so that we can look at the next process we can attempt to use to solve. So in the next one, we're going to try to solve by factoring. Factoring, actually, it's going to be used in a few other problems that we see moving forward, but when you're seeing a square in here, that's a hint that you may want to try to factor. Not always. Sometimes it will be telling you to use Pythagorean identity, but the Pythagorean identities are when we're looking for like a sine squared and a cosine squared, so we have multiple trig functions. If you have a single trig function, like in this equation we only have sine, and you see a square in there, think about quadratics and trying to factor, okay? So when we see a single trig function squared, you want to be thinking of factoring. Okay, so in this case, if we want to try to factor, remember, just like with the quadratic, we want everything on one side and equal to 0. So I'm going to leave this sine squared x here, and let me actually move it. If I move these terms over, if I subtract over the sine of x and subtract over the sine of x, that would cancel there, and these are like terms. That would give me negative 2. I wanted to go back to blue. That would give me negative 2 of those sine of x's, and then I'm going to also subtract over the 3, so it'll be a minus 3 on this side, and now equal to 0. Okay, so I got it all on one side and equal to 0. And now factoring, when it looks like this, might be a little hard for you to envision. So I'm going to use substitution here for just a second. Instead of sine squared, let's say this is like a squared. And then instead of sine, again, let's just say that this was 2a, and then minus 3. We're going to factor this expression that has the signs in it the same way we would factor a squared minus 2a minus 3, where factors of negative 3 that make negative 2 would be a negative 3 and a positive 1. So this will work the same with our signs. Instead, in place of a, we're going to have sine of x. So when we factor this, it's going to be the sine of x minus 3 and the sine of x plus 1 equal to 0. So now it's all factored. And remember, the point of factoring is to be able to find where the whole equation is equal to 0. We make that happen by making just each factor equal to 0. So that's the same concept here. Now that it's in factored form, if I can make each of those factors equal to 0, then I will find my solutions, or my solution sets. So I want to know, where is the sine of x minus 3 going to equal 0? And where is the sine of x plus 1 going to equal 0? Or where is the sine of x going to equal 3? And where is the sine of x going to equal negative 1? Well, the sine of an angle can't equal 3. Remember our sine curve, and think about the unit circle too. The sine curve starts at 0, goes up, comes down, hits 0 again at the end. But what's the max? The max it can be is positive 1. The min it can be is negative 1. So finding the sine of an angle at being 3, it's just not going to happen. The maximum value for sine is 1. So this one's not going to produce a solution. It's not possible because the max for sine of an angle is 1. So that's not possible. And over here, the sine can definitely equal a -1. That's our minimum, right? And where does that minimum happen? Where's our minimum sine, or where is sine -1? Well, that happens at 3 pi over 2. And it happens every time we make a full circle. So 3 pi over 2 plus 2 pi plus another 2 pi. And however many times I want to go around the circle, I'm going to land in that same spot. And so we're going to say, oops, this one happens at x equals 3 pi over 2 plus 2 pi n number of times. Okay, so that's going to be our solution set for this problem. All right, hopefully we're feeling okay so far and moving right along. We're going to try to introduce some identities into the next one. So actually here we're going to use identities and factoring. Now when you're seeing, again, so far everything has had just one trig function in it. When you see your equation with multiple trig functions, so looking at 5, looking at 6, we see sine and cosine, that's going to be your clue to use identities, okay? So we're generally going to be using identities when there are multiple trig functions, when we have more than one trig function. Alright, so here, for instance, we have more than one trig function. The goal would be to use an identity to get it in terms of only one, not the two that are here. And when I'm seeing cosine squared, I know immediately I can use the Pythagorean identity. So we know that cosine squared x and sine squared x together make 1. So I can replace cosine squared x with, if I subtract this over, 1 minus sine squared. So I'm going to leave the -2 in here. I'm going to replace cosine squared x with 1 minus sine squared. So 1 minus sine squared x. And I still have this plus 1 equal to sine of x. So I made a substitution here, Pythagorean identity. I substituted cosine squared with 1 minus sine squared. Okay, now, because I have, this looks just like, to me, looks just like number 4. I have a sine squared in there, I have a sine to the first in there. It's all one trig function now, and I have a square, which is telling me I need to try to factor. So I'm going to distribute. This is going to be -2 plus 2 sine squared x plus 1, and I'm going to subtract the sine of x over to get it equal to 0. And now I'm going to put it in order and combine like terms. So I have 2 sine squared x, and then a minus sine of x, and then a -2 and a positive 1 makes a -1 equal to 0. And just because it's hard to see it sometimes trying to factor from this form, think about this as 2 times a squared minus a minus 1. If we were trying to factor that, we would be looking for factors of -2 that make -1, and then we would divide them by 2. So this would factor into a minus 1 and 2a plus 1. And now we can go back and say, okay, instead of a in there, we need to have sine of x in there. So this will factor into the sine of x minus 1 and twice the sine of x plus 1. And if I can make each of those factors equal to 0, then I can make that entire equation equal to 0. So we want to know, where is the sine of x minus 1 going to equal 0, and where is 2 times the sine of x plus 1 going to equal 0? Or where is the sine of x going to equal 1? And over here, if I subtract the 1 and divide the 2, where is the sine of x going to equal a -1/2? All right, so back to my unit circle. Unless by now you're getting to know this pretty well. Where is the sine of x equal to 1? So sine is our y value. Sine is going to be equal to 1 right here at pi over 2. at pi over 2, and every time I make a full circle, that's going to repeat. So pi over 2 plus 2 pi n times. Oops, I just deleted. Okay, so sine of x is going to equal 1 at pi over 2 plus 2 pi n times. And that size is a little off there. Okay, let me write that again. Pi over 2 plus 2 pi n number of times. So that's going to be part of our solution set. That's one part of our solution set. And then where is our sine equal to a negative 1/2? Let me go back to the unit circle. So where is our sine going to be a negative 1/2? Sine is a negative 1/2. I can see a negative 1/2 here. And sine is also equal to a negative 1/2 here. So a couple ways to capture this solution set. Since we have two different ones, I would probably state one as a positive and one as a negative. If it's just one, just state the one, right? But let me deal with this one first, okay? So we have 7 pi over 6, and again, every 2 pi, that's going to repeat. So we can say we're going to have 7 pi over 6 plus 2 pi n. And then the other one happened here at 11 pi over 6, but I've already got a positive one, and it would be okay to use that as a positive as well, but I like to just, if I have two, give a positive and a negative if I can. And so I'm going to call this one negative pi over 6, right? Instead of positive here, it's going to be negative pi over 6. And then again, every 2 pi, that's going to repeat. So 7 pi over 6 and negative pi over 6. And let's go back. So x is going to equal 7, I didn't write that right, 7 pi over 6 plus every 2 pi, that's going to repeat. And then also negative pi over 6, and again every 2 pi, that's going to repeat. So we have 3 infinite solution sets for this one, which is, it's like kind of mind-blowing to think about that. And I just feel like, yep, no, okay. That's a lot to take in, but there it is. All right, let's look at the next one. We're going to use an identity again, but and I know I'm going to have to use an identity because I have two separate trig functions in here. But there's a couple things happening with this one. First, it says to solve, well, we're going to solve, that was sort of the direction for all of these, but there's a difference here. This one says to solve on the interval from 0 to 2 pi. Now, when you're restricted to an interval like that, 0 to 2 pi, that means you're only looking at one full circle, and you're not even looking at the endpoint of the circle. So we don't have to worry about adding you know, a 2 pi n or pi n or anything like that to it, because we're only going to look at one cycle here, right? So that's one difference. Another difference is here, I don't find it as easy to swap out just a sine or a cosine. A lot of our identities involve sine squared, cosine squared, and so what I would probably do on this one is square both sides. So I'm going to start this one by squaring both sides, because I can easily replace sine squareds and cosine squareds. Now, we do have to be careful. When we square both sides, we introduce the possibility of extraneous solutions. That was true before, right? When we solve like a radical equation, if we square both sides, we could get a solution that doesn't actually work. So this introduces possible extraneous solutions. So it's a hiccup, you know. Just means we're going to have to check our answers when we're all said and done here. So let's do it. If I square this side, if I multiply the sine of x minus 1 by itself, and then I square this side, that's easy, cosine squared x, we're going to end up with a sine squared x, and then a negative sine of x and another negative sine of x, which makes negative 2 sine of x, and then a plus 1 equal to cosine squared of x is going to go away, okay? I did this so that I could try to remove one of the trig functions from the picture, and again, cosine squared x is 1 minus sine squared, just like the last one, so I'm really using the same replacement here. So I'm going to make this, I'm going to do this in one step. I'm going to replace cosine squared x with 1 minus sine squared. And again, that was a substitution. Okay, so because now this is all in terms of one function and I see squareds in there, I'm going to try to factor. So let me get everything on one side and equal to 0. If I add this sine squared to this side, the 1 here plus the 1 here is going to give me 2 sine squareds. And then I have this minus 2 sine x. And then when I subtract the 1 here, it's going to cancel from both sides. So this is it. These two terms equal to 0. All right, so this is factorable. I can take out 2 sine of x. That's going to leave me a sine of x minus 1. And now that it's factored, I can make each of those factors equal 0 to get our solutions. So what makes 2 sine of x equal 0? And what makes the sine of x minus 1 equal 0? So over here I'm going to divide over the 2, so I'm still looking for what makes the sine of x equal 0. And over here I'm going to add over the 1, so what makes the sine of x equal 1. Okay, back to the unit circle. I'm looking for where is the sine equal to 0. And remember, this is on the interval. It told us only to go from 0 to 2 pi, and it said don't even include the 2 pi. Okay, so we're looking at a full circle, but not the end point there. So if we're going from 0 to 2 pi, but not including 2 pi, where is sine equal to 0? Is going to be at 0 and at pi. So two solutions so far will be at 0 and at pi. So x is equal to, let me zoom in so I can get this the same size, x is equal to 0 and x is equal to pi. And then where is our sine equal to 1? Let's go back and look. Where is our sine equal to 1 in this one circle? Sine is equal to 1, sorry, right here. That was terrible, at pi over 2 radians. Okay, so pi over 2 is the other possibility. And so here I'm going to say x is equal to pi over 2. Now, because I squared both sides in the beginning, I have to test all three of these in my original equation to make sure I don't have an extraneous solution sitting here. So I need to check them. So I'm going to check. Got to plug into my original equation. So sine of x minus 1 should equal cosine of x. So the sine of 0 minus 1 should equal the cosine of 0. Well, the sine of 0, if you need your unit circle, okay, your sine of 0 is 0. That's how we ended up with that anyway. So 0 minus 1. Well, the cosine of 0 is 1, and negative 1 does not equal positive 1, which means that's an extraneous solution. So 0 is extraneous. Okay, and let's test pi. If I test pi, the sine of pi minus 1 should equal the cosine of pi. So the sine at pi is going to be 0, and the cosine at pi is going to be negative 1. Well, negative 1 does equal negative 1, so that's a valid solution. I'm going to box that one in. And then let's check the last one here. The sine of pi over 2 minus 1 should equal the cosine of pi over 2. So the sine at pi over 2, or that's the sine at 90 degrees, is going to be 1. And the cosine at pi over 2 is going to be 0, and 0 does equal 0. So this is going to be a valid solution for us as well. Okay, so we got one extraneous and we got two valid, so we're just going to keep those two valid solutions, which, man, that looks like when I zoom out, it looks like a lot of work for that one problem. I hope you're doing okay on the other end of this video. Now, I want to show you another way to solve graphing, which I think is a very intuitive way to solve. If you're back in my day doing this on a calculator was not so nice, but Desmos, it's just wonderful because it does everything so cleanly. So if I wanted to solve by graphing, I'm going to do, let me get rid of this. Sorry. I'm going to do, what I'm going to do is graph each of these, each side of the equation as a separate function. So I'm going to graph this as y equals the sine of x, and I'm going to graph this as y equals the cosine of x, and I'm going to look for where they equal would be where would those two intersect. So find the intersections. And this is again just on the interval from 0 to 2 pi, so I don't have to look forever, just over one cycle basically. So let's type this in here. Oops, y equals the sine of x, and y equals the, come on fingers, cosine of x. Okay, so here, and let me just go ahead and fix my window just so I know I'm looking in the right spot. So I want to look at just 0 to 2 pi, and let me just go by pi over 2 because that's pretty standard. And then, like -2 to 2 is going to give me enough of my picture here. Okay, so now that that's gone. So here's my graph basically from 0 to 2 pi. So I don't care what's happening before 0. I don't even care what's happening at pi or after, just in between there. So where these two are going to be equal is where they intersect. And if you tap on those intersections, it gives you, Desmos is so nice, it gives you the exact values. So I know that x is going to equal, the x value in that first intersection was pi over 4. And then right here is our second intersection, and that x value is our second solution. So x is equal to 5 pi over 4. And we don't have to worry about repeating those because we're only looking at that one cycle from 0 to 2 pi. So there it is. That, to me, is the easiest way to graph, and you can try to apply that to other situations as well. It's a nice way for you to try to verify your work. Okay? It's just hard when the cycle goes for, or the functions are going forever. You have to kind of keep repeating. In my opinion, it's easier to just use the unit circle, but graphing in Desmos is a good option for you too. Okay? Last ones we're solving using inverse trig functions. That's where we get rid of a sine by taking the inverse sine, or we get rid of a tangent by taking the inverse tangent, but the other strategies are going to come into play here as well. So, looking at this equation, I might not know just by looking at it that I'm going to have to use an inverse trig function. So thinking about my other strategies, it's only got a tangent in it, and I see a square that's telling me to try to factor. So tangent squared x plus 2 tangent of x. I'm going to subtract the 3 over, make it equal to 0. And this is just like trying to factor a squared 2a and then minus 3. This would factor into a plus 3 and then a minus 1, which means our tangent expression up there is going to factor into tangent of x plus 3 and tangent of x minus 1. But now that it's factored, my solutions are going to come from what makes each of those factors equal 0. So what's going to make the tangent of x plus 3 equal 0, and then what's going to make the tangent of x minus 1 equal 0? Or in this case, what makes the tangent of x equal -3? And in this case, what makes the tangent of x equal 1? Now, we saw one earlier where we had sine equal to 3, or if it was sine equal to -3, neither one of those would have worked because sine has a max and min at 1 and -1. But remember tangent, we have these branches that go up and down forever, and so we don't have to worry about the restriction here because it doesn't have a max or a min, okay? But we do have the issue of there isn't a place on the unit circle where our tangent is going to be -3. Our tangents are y's over x's. We end up with radical 3's in all of them unless it's a 0. It's one of our, let me go to the unit circle so I can not try to watch this when I'm explaining. So if we were to find tangents in any of these spots, so we get 1's here, we get radical 3's in these, y over x, this would be undefined, and this would be 0, so 0 or 1 or undefined or radical 3's, but nothing that's just going to be a 3 or a -3. So that's not going to be an exact place in our unit circle, which means that is the perfect place to just use the inverse tangent. So if the tangent of x is going to equal -3, then we can say x is going to equal the inverse tangent of -3. So we get rid of tangent using its inverse. And so that's the exact solution there, approximately. Let's see. Inverse tan of -3, about -1.249-ish. looks good to me. So that's going to be one part, one solution there. And then tangent of x, where is that going to equal 1? Let's go back to our unit circle. That was a possibility. Tangent, remember, is y over x. So where is y over x going to equal a positive 1? So that's going to happen here, and then technically it's going to happen again every 180 degrees, but I think this one was restricted as well. So I don't think I need that. Let me go back. Oh man. Sorry. I always swipe and erase, and I don't mean to do that. Okay. Yes, this one was restricted from negative pi over 2 to pi over 2. So we said tangent was going to be equal to 1 right here, and that's, so from pi over 2 to negative pi over 2, that's this area here. So I don't want to actually go that far. So in that window, the only place where our tangent is equal to positive 1 is pi over 4. So that's going to be the only solution for that one. Now let me go back and say here that x is going to equal pi over 4. So we have two distinct solutions for this guy. Okay, last one. And we're hanging in there, I hope. So this is another one that's restricted, which is good. Less solutions for us to have to try to manage here. This only has one trig function in it, so I'm not having to worry about using an identity to replace anything. And so let me just try to isolate this. I'm going to subtract this over. If I subtract my sine of x over, if I have 6 of them and I take the 1 away, then I have 5 sine of x minus 2 equal to 0. Well, that's not a square or anything I want to try to factor. I just need to get that sign by itself. So I'm going to add the 2 over. So 5 sine of x equals 2. And then I'm going to divide the 5. So I'm looking for the sine of some angle to be equal to 2/5. Now that's not 2/5, not going to be a place on our unit circle. So let me just draw this out to make sure I don't miss anything. I know I could take the inverse sine, but I just want to make sure I'm not missing anything. Okay, so think about what's happening here. Oops, let me cheat tool, draw this kind of nicely here. The sine is actually going to be positive, so on the interval from 0 to 2 pi, we don't actually have to go full circle, because we have sines. Remember, sines are y values. Y values are positive in quadrant 1 and in quadrant 2, but they're negative here and here, so I don't have to go full circle. If I have any answers, they're going to be in this first quadrant. But this is why I'm drawing this out, because if I just took the inverse sine, I might only capture one solution, but it looks to me like there's going to be 2 here. If I have a triangle in this quadrant, let me change colors. Okay, so if I drew out my triangle in this quadrant, okay, what we're saying is if we have an angle here, which we're calling x in this thing, that the sine is 2/5, so that means the opposite side is 2 and the hypotenuse would be 5, right? Well, in the second quadrant, I could make that same picture, right, where we have the same reference angle with a opposite side of 2 and a hypotenuse of 5. So it's the same reference angle, but technically, what is the measure of the actual angle? So this angle here is x, but this angle here, this is the same reference angle, but the entire angle here is how much? Well, it's 180 degrees would be the whole distance, right? So I actually have to take that 180 degrees or that pi and subtract out the x. So this is actually pi radians minus x in there, if that makes sense. Okay, so one of our angles is x. The other angle is 180 degrees minus x, or pi radians minus x. So there are two triangles where this can happen. There are two angles where the sine of our angle could equal a positive 2/5. So let me see if I can make this make sense. Hopefully the picture is making sense. What I'm saying is that the sine of x can equal 2/5, and that the sine of, I should probably change colors, sorry. the sine of x, and then the other angle is the sine of pi minus x. And I don't have space for what I'm trying to do here. And let me just move this so sorry, trying to move all this so it doesn't all collide. Okay, so the sine of pi minus x is also going to produce that same triangle. So we're going to get two solutions here. This one, I have to take inverse sine. That's the only way to actually get a value here because it isn't a place on the unit circle. So we're going to say that x is going to equal the inverse sine of 2/5. And if we didn't draw this out, that would have been the only solution, but we can see that that same triangle occurs in both quadrant 1 and quadrant 2. So the other one here is going to get us our other solution. So in this one, it's actually pi minus x equal to the inverse sine of 2/5, right? So I take the inverse sine, basically, of both sides to get rid of the sine, but I still have to solve for x. So I'm going to subtract pi over, and then I'm going to divide, subtract pi over, and then I'm going to divide over the negative. So we have a positive pi minus the inverse sine of 2/5. That is our angle in quadrant 2, and this is our angle in quadrant 1. And that is a mess. That's probably one of the tougher ones of all of these. Like, how are you supposed to know that, that you're looking for two separate angles there? You really should be thinking about the sine, not like S-I-N-E, but S-I-G-N, right? If we're looking for sine of an angle to be positive, that can happen in two quadrants, so we should be looking for two answers. Or if it was cosine, cosine would have been positive here and here, so we've been looking at those two quadrants. So we had lots of little details for us to be paying attention to. Okay, so I've given you I think more than enough examples. I'm sorry if it feels a little overwhelming. Hopefully you'll find the practice to not be too complicated. I'm going to try to mirror some of these problems. This is just for some exposure, okay? It takes a lot of practice to get really good with these, so do your best, and if you find yourself needing some extra help, then just reach out. Alright guys, take care.